beaming internet from the middle of the woods using an extra-large pizza-sized satellite dish placed on top of your house up to a satellite orbiting 550 kilometers outside Earth's atmosphere, well, let's be honest, is technologically mind-blowing. What's even crazier is that the Starlink satellites move incredibly fast, around 27,000 kilometers per hour, and data is being sent back and forth between them at hundreds of megabits per second, all while the dish and satellite are continuously angling or steering the beam of data pointed directly between them. On top of that, the dish switches between different satellites every 4 or so minutes because they move out of the dish's field of view rather quickly. If you have no clue as to how this is possible, stick around, because we're going to dive into the multiple key technologies which enable satellite internet to magically work. First, we'll explore inside the satellite dish and see how it generates a beam of data that is able to reach space. Second, we'll see how this dish continuously steers the beam so that it points directly at a satellite moving across the sky. And third, we'll dive into what exactly the dish and satellite are sending inside the beam that results in your ability to stream 5 HD movies or shows simultaneously. This video is quite long as it's full of in-depth details. We recommend watching it first at 1.25 times speed and then a second time at 1.5 speed to understand it as a complete technology. So stick around and let's jump right in. First, let's start by clarifying the difference between a television satellite dish, such as this one, and the Starlink ground dish, which Elon Musk dubbed Dishy McFlatface, or Dishy for short. TV dishes use a parabolic reflector to focus the electromagnetic waves, which are the TV signals sent from broadcast satellites orbiting the Earth at an altitude of 35,000 kilometers. TV satellite dishes only receive TV signals from space. They can't send data. Dishy, however, both sends and receives internet data from a Starlink satellite orbiting 550 kilometers away. While the Starlink satellite is 60 times closer than TV satellites, it's still an incredible distance to wirelessly send a signal, and thus the beams between Dishy and the Starlink satellite need to be focused into tight, powerful beams that are continuously angled or steered to point at one another. Compare this to TV broadcast signals, which come from a satellite the size of a van, and whose signals propagate in a wide fan that covers land masses larger than North America. Table-sized Starlink satellites, however, need to be in a low Earth orbit to provide for 20 millisecond latencies, which is critical for smoothly playing internet games or surfing the web, and as a result, their coverage is much smaller. Thus, 10,000 or more Starlink satellites, all orbiting at incredibly fast speeds in a low Earth orbit, are required to provide satellite internet to the entire Earth. Let's now open up Dishy McFlatface. At the back, we have a pair of motors and an Ethernet cable that connects to the router. Note that these motors don't continuously move Dishy to point directly at the Starlink satellite. They're used only for initial setup to get the dish pointed in the proper general direction. Opening up Dishy, we find an aluminum structural backplate, and on the other side we find a massive printed circuit board or PCB. One side has 640 small microchips and 20 larger microchips organized in a pattern with very intricate traces fanning out from the larger to smaller microchips, along with additional chips including the main CPU and GPS module on the edge of the PCB. On the other side are 1,400-ish copper circles with a grid of squares between the circles. On the next layer, there's a rubber honeycomb pattern with small, notched copper circles, and behind that, we find another honeycomb pattern, and then the front side of Dishy. So, what are we looking at? Well, in essence, we have 1,280 antennas arranged in a hexagonal honeycomb pattern, with each stack of copper circles being a single antenna controlled by the microchips on the PCB. This massive array works together in what's called a phased array in order to send and receive electromagnetic waves that are angled to and from a Starlink satellite orbiting 550 kilometers above. Let's zoom in and see how a single antenna operates. Here we have an aperture-coupled patch antenna composed of 6 layers, most of which are inside the PCB. It looks very different from the antenna of an old-school radio, and is honestly incredibly complicated. So let's simplify it. We'll remove a few of the layers for now and step through the basic principles of how we generate an electromagnetic wave that propagates out from this antenna. To start, at the bottom we have a microstrip transmission line feed coming from one of the small microchips. This transmission line feed is just a copper PCB trace or wire that abruptly ends under the antenna stack. We send a 12 GHz high-frequency voltage or signal to the feed wire, which is a voltage that goes up and down in a sinusoidal fashion, going from positive to negative and back to positive once every 83 picoseconds, 12 billion times a second, or 12 gigahertz. Note that high-frequency electricity works differently from direct current or low-frequency 50 or 60 Hz household electricity. For example, above the copper feed wire, we have a copper circle with notches cut into it called an antenna patch. With DC or low-frequency alternating current, there wouldn't be much happening because the patch is isolated. But with a high-frequency signal, the power sent to the feed wire is coupled or sent to the patch. How exactly does this happen? Well,